So, welcome everybody. Today we'll discuss reservoir characterization. So, whatever we discussed so far for acquisition of different data by different means, we discussed about the fluid data acquisition. We discussed about petrophysics and reservoir characterization, reservoir data acquisition by means of a well log. Then we discussed about dynamic data acquisition by well test analysis, and we also discussed the petrophysical aspect also. So the purpose of reservoir characterization is to capture the features that determine the fluid flow in the reservoir and affect production profile and hydrocarbon recovery. So that means initially we may have very limited data, but with time, as time progresses during the production, or maybe as we do lot more activity during data acquisition, so with time we try to understand the reservoir in much better way with the help of the new data. Okay. So what actually reservoir characterization attempt to answer the following question. So actually why we do reservoir characterization? Then we try to understand actually what are the limiting factors in oil recovery. What are the factors which actually not helping us to recover more? What can be done to improve recovery and or oil rates? So what we have to do, that means individual well, sometimes field wise we need to see what are the problems actually we are facing, so that individual well or maybe the field is not producing at its optimum level. Where do we make changes? Really, is there any scope to change certain modifications in the system which is still existing? Are the changes proposed economically viable? That means everywhere, whenever we discuss anything, we need to see the economics part in a much greater and in a greater way. So that's why whenever we are discussing for reservoir characterization, we need to take care all the parameters or data which we acquire so far. So reservoir characterization involve combining all the reservoir data to form a 1, 2 and 3 dimensional representation of the reservoir. Always we discussed about the static modeling as well as dynamic modeling. So that means you require a lot of data to understand the specific reservoir dynamics, so that we could really understand the reservoir performance better. Okay, so this model can be mental model, that means it's our visualization with the help of data, analytical, geological or flow simulation model. So that means with the help of all the parameters we try to visualize what is our actual reservoir, what is the type of flow occurring inside the reservoir. So we need to incorporate data of fluid type. We have discussed in a lot more details regarding the type of fluid we may encounter into our reservoir. Reservoir architecture, size and structure, porosity, permeability, saturation distribution, everything. Okay, sometimes this is called the rock model, where the structural model characterizes only the structural aspect. So what geological model encompasses everything, whereas this is generally static model. So what structure, porosity, permeability, when you put the permeability and flow behavior, then it is considered to be a very dynamic model. Okay, so because we have already discussed the drive mechanism, the support system, or what are the type of support system existed into the reservoir, that also we could understand with the help of our either you can say your volumetric reservoir, particularly material balance calculation, or sometimes with decline curve analysis also. Okay, the flow mechanism characterization. So what, combining all the parameters, we try to understand the 3D model as well as their drive production mechanism. So this is the main purpose of reservoir characterization. So these are what you see, these are guidelines. Depending on your type of reservoir, that is particularly drive existed in the reservoir, we generally do certain reservoir performance analysis. So you can see here, if it is an expansion drive, so you can do the material balance or material balance and the decline curve analysis. Okay, so if you have a solution gas drive, then depending on the solution gas drive, segregated, okay, homogeneous or layered, pocketed. So that means depending on your type of drive mechanism as well as your type of reservoir, you should use your different analysis model. So it may be material balance, it may be decline curve analysis, it may be simulation model also. Sometimes you need to take care for your understanding your reservoir production. Okay. Then if you have a gas cap, you see the gas cap, if you have a gas cap, depending on your situation. So guidelines is, if it is segregated gas cap, non-segregated gas cap. If it is a non-segregated gas cap, So you can understand by different means. It's a simulation model. You may have material balance, decline curve analysis. Then you can use the Koenig model also to understand how the reservoir actually helping. So what it is, a mental model, it is a geological model, it is a simulated model, it is a dynamic model. So that means with addition of new information in different form, actually we need to understand specifically the reservoir production mechanism. Okay. So if it is water drive, so you may have a weak water drive, you may have a strong water drive, you may have your bottom water drive, you may have an edge water drive. So depending on the support system existing in your specific reservoir, different way you could understand your reservoir performance. So one is your, what we have discussed earlier, the volumetric reserve estimation, the very early understanding of your reserves. Then with the subsequent time, when you start taking your production, you can do your material balance calculations for understanding reservoir performance. Then when more or less you have some amount of production, you start declining, then or maybe you are getting a follow particularly declining, then we generally use the decline curve method. And in time also, in each and every time, depending on the availability or of our reservoir data, we use simulation. So in early time, if you have less data, that time we could not use simulation in that way because data population is not that strong. Okay, but with time maybe we may rely very much on the simulation model also. So that is how we try to understand our. Okay, so this is, you just in sum up. So characterizing a reservoir from what we are usually partial and inconsistent data is probably the greatest challenge in reservoir engineering. So what we discussed during our different topic, when we discussed, we acquire data in sporadic way in different times. Okay, so that's why data inconsistency is very much challenging when we are really trying to understand a reservoir mechanism. So you may have less geological data, we may have less geophysical data also. So combining all the, so we try to understand our reservoir, how in terms of their structure, in terms of their geology, in terms of their flow behavior, in terms of their connectivity, in terms of their drive mechanism. So we can use volumetric methods. We discussed where we could calculate by material balance calculation. Sometimes in the early stage I discussed, when we try to develop a field, that time we generally use the field analogy. That means the field is alike of other fields, very similar in size, shape, their geology, structure, everything is. So analogical part also sometimes we use for understanding the reservoir performance. Decline curve analysis, then we sometimes we develop analytical model for understanding our reservoir performance. Okay, so and then simulation. So however, any one method is likely to provide a large range of possible solutions for the oil in place, expected production rates and recoverable reserve. So that means it is not a single method by which you could be so confident. So that's why what simultaneously we need to perform different analytical methods or maybe the calculation method to understand the actual reserves. Then with time maybe we are modifying the reserves, but with time we may be more confident about the particular reserve drive mechanism, production mechanism, and the future recoverable reserves. That means the prediction. Okay, so if you just go through the Venn diagram, it would be easy. So different parameters, actually different data helping us to understand much better way. So seismic log core, spatial core, PVT is helping us to understand the volumetric reserve estimation particularly. Well data, production, pressure transient test, PVT, reserve production performance with time, that can give us. When we do the material balance, we discussed about material balance. That means with production, how the pressure is decreasing and how the PVT parameters are changing. So that means when we combine all our calculation scheme, sometimes we may be in a very individual is not helping us to understand much better way. But once we mix up all the methods, then maybe some accurate solution we may get with a specific accuracy level. Okay, so this is what is the very important part. So being a geoscientist and engineering field, you must be aware how by using different parameters we try to close or we try to reach closer to our reality. That means in terms of the reservoir structure and performance wise. So once you see the different stage you have discussed, is in the early stage of exploration, then we go for development and then we do our optimization. You see the result, recoverable reserves. Initially, when we have very limited data, that time you see the recoverable reserves very high. But once you start developing your field and try to acquire more information or more data, you see your reserves is now decreasing. Okay, that means you are taking production. So right from here, you see the reserves is now in the declining. That means you are getting more accurate information regarding your reserves in terms of the areal extent. Then there are so many problems in between. Okay, when we do the development, you see your production rate, you are increasing your production rate, then cumulative oil production you are increasing, so your residual recovery, or maybe you can say the rest of the reserves is still very less. And how we are going to develop this part, that is actually the shape of the graph will change according to our development procedures or method. So reservoir characterization are periodically updated. So that means what is happening each and every time of our development, we acquire more data, more information, more characteristics value, so that we go closer to the reality of a reservoir in terms of structure, in terms of dynamics, in terms of the support system, everything, so that we do better work for our optimization. Okay, so this is what, if you say reservoir characterization team must then judge which interpretation is most likely, but also must be flexible in its thinking. In most, if not all cases, several iterations are required to obtain a satisfactory characterization. Often there is insufficient data to perform the full step-by-step analysis, and the reservoir engineers and reservoir characterization team must adjust their approach according to the data available. So it's a very important aspect of in reservoir engineering and particular development geology. So if you cannot properly analyze your reservoir in terms of their structure, architecture, characteristics, fluid behavior, production behavior, so good engineering and geoscience information actually based on the data only. So compensate the lack of data. So good engineering and geoscience work will not fully compensate for lack of data. So data is the real information for the reservoir. So you may have a good understanding about the reservoir, but if you don't have sufficient data, sometimes you cannot compensate with your knowledge. Okay, so this is what, whenever we are working for developing a field or trying to manage our reservoir by doing so many activities, we must be careful when we should acquire data in a specific manner and a sequential manner. What should be required? Okay, so you see here how ratio is changing with time. So you see, this is discovery, this is the timeline. Okay, and we are changing our activities. So if you see discovery, start on production, reserves with write down, okay, reserves, the reserves update, water flood, new seismic, EOR. So that means with time you see the new data we are acquiring in different perspective actually. Okay, so then what, with time we are acquiring different data and then trying to analyze our reservoir with the addition of the new data, reanalyze it, remodel it with the new data, and then we try to implement or try to increase the production, or try to increase the, or try to put in the optimum production level. So particularly for large field, there may be a changes in recovery factors due to mandate factors as shown in figure. So you can understand. Okay, so what sometimes regulatory board actually put some mandates for the operating organization. So that's why you should be careful enough. Are you really following up your mandates, what is given by the regulatory board? If you are not following, then you may have to give some sort of penalty for this also. Okay, so changes to apparent reserves, probably distribution due to operational changes, and update reservoir characterization view over time. So you can see this reserves, write down, reserves, update. That is what is happening each and every time with addition of new well, or maybe exploratory step out, or maybe new drilling, we change the reserves. Okay, so this is called reserves update or reserve updation. So this is how each and every step reservoir engineers along with their development team, all people are working together to understand particularly or updating the information in terms of the all the parameters of the reservoir. So stages of reservoir development and associated activity. As we discussed, we need to understand the reservoir. Okay, reservoir characterization is the first important part, where you need to give the input for your rock, your fluid, structure from your seismic profile, maybe from geological information, maybe the well correlation, log correlation, everything. So once you try to understand this is reservoir static model. Once you put your data, then you are getting a dynamic data, then you are getting a dynamic model. So generally, geology people are responsible for preparing the static model, where the reservoir engineering people will put the information for static model. But if you work in specifically in a development geology, you must know both the things together so that you work in a better way. Okay. So once you do, then what you are adding up your drilling domains. That means what? This is a development activity. That means you whatever reserves you have, you try to acquire the reserve specifically, or you try to exploit the reserve. So what? You are drilling a new well, then you are developing facility, you are completing it, and then again with the further addition of data, you are changing your development plan. Okay. So then field management, production operations. So what? These are all in loop. So once you get this development plan, is not once, it can be repeated in many times. Okay. So then you are reviewing your performance, then maximize the value. Again the same loop may follow. Okay. So you see the depletion and plant optimization. So again you are coming back with a new addition of data and going again for the same sequence. So that is now in the life of a field, it is not only a one time, it may be many time. We addition of new data, we change our development plan. It may not be many times, but it is a reasonable time, 3 4 time, 5 times also. Okay, depending on that, we just prepare this loop and refine our all the models, static and dynamic, and then optimize your production. So components involved in the reservoir characterization process. So already I discussed this part. So you see initially all the data. If you just see it here this part you have core data, log data, fluid data, PVT, pressure data. This is actually pressure transient. You can see fluid characterization, fluid flow characterization also. That means the reservoir understanding. Then this is actually what the production history, production people, that means at what rate the well is producing. So initially all the data is involved, or we generally require all the data for our, you see this data for rock characterization, this data for fluid characterization, and the fluid flow means reservoir characterization. So once you understand, you are preparing your geological model, then you are doing your all the calculation scheme. Okay. So your volumetric reserve estimation, material balance. Then once you understand the recoverable reserves, then what? You are checking the consistency check. Consistency check means you are trying to match it with from different parameters. Is it really my reserves are recoverable reserves are matching or not? Once not, you are predicting for the future production, rate of production, or what other wells you are going to drill. Then once what you will come back again. If you are not consistency check is not there, again you are adding up new data, trying to understand the reservoir much better way. Then again you are putting it. So this is a cyclic process. Cyclic process up to a certain level for taking any decision. Once you do it, go for some times and then repeat with the addition of new data. Okay. So recommended workflow for brownfield. Brownfield is the old field. Okay. So initially what we discussed for your specifically early field, you may have to see for the analogy relations with other fields for the production. But in case of brownfield, determine fluid type from fluid analysis and PVT studies. Okay. Determine the type of reservoir drive mechanism by examining field and area production profiles if available. Develop a structural model from geological discussion and the modeling mapping. So that means these are the constant process. You see locations of the gas oil contacts, water oil contact. That means you are trying to visualize a specific model for your reservoir based on the data available to you. Okay. So now develop a permeability model from geological analysis and modeling mapping, concentrating on net pay, permeability maps, and porosity maps. So we have discussed already during our last semester also and this semester. So what you need to understand the well information to your three-dimensional reservoir information. That means you need to upscale your information. So where there you need to put the geological information, okay, to understand specifically your different maps, particularly the net pay thickness map, permeability map, porosity map, so that what this will give us your information how the porosity is distributed throughout your reservoir, how the permeability varies in each and every domain of your reservoir. Okay. So determine the fluid flow patterns by examining aggregated individual well performances. So this is one part when we are producing from a well. Generally the well have a specific optimum production rate. That individual well production with oil, gas, and water may help us to understand particularly the well performance, individual well performance. So communication if wells are close proximity have similar behavior in terms of GOR or water cut. So these are the parameters. There is production parameters you can judge and get the connectivity, or you can do the well test data to understand the specific dynamic relations between the wells. Okay, so if wells or groups of wells behave differently in terms of GOR or water cut or oil decline behavior, check if the behavior is a top structure or distance from the gap, or in between there is a discontinuity. So what these are all we have discussed about. You see the GOR pattern is following same. So that means once pressure is decreasing, so well aggregated plot means you are trying to understand all the wells in this aggregates or in this area are similarly behaving. That means they are in well communications. If their behaviors are not same, that means they are not in communication. So determine how operational effects, changes in the flowing pressure and rate of changes have affected the production profile. That is what these are the points you need to take care to understand your reservoir domain, or you can say segments. Select the development strategy to be used. For example, continue primary solution gas deficit. That means what? If you have segregated your area in terms of their performance, in terms of the structural pattern, in terms of their behavioral pattern, now you cannot go for a specific type of production for each and every domain or area or blocks. Okay, so that what you have to do, you need to follow specific pattern for the specific type or specific domain. Okay, so this is an analogous reservoir. So this, in the early stage when we don't have much information, we can use an analogous reservoir. Then the same field production or performance we could use for understanding the performance of our reservoir where the data is not sufficient. Update the reservoir characterization with new production data. So this is a cyclic process I told you. So that's why you just do the cyclic process with the addition of new data and follow the same procedure for understanding your reservoir characteristic in terms of performance behavior with addition of new data. So conduct the development and operation of the reservoir so that ensure the maximum possible efficiency in the oil recovery. So this is what, for this specific part, we are trying to understand our reservoir, acquiring a lot of information in the static condition and the dynamic condition of the reservoir. Okay, so this is what is very important for us to understand the philosophy behind understanding the reservoir mechanism. Once we understand the reservoir mechanism, then our development strategy should be very effective. Otherwise, it is not going to be effective. So this is the same workflow. We are discussing fluid properties, dry mechanism, reservoir architecture. Then you are putting a permeability and porosity model. Then your flow characteristics. That means what? Ultimately, your well information is now upscale. You are upscaling to a three-dimensional reservoir so that you properly understand your reservoir in terms of static as well as dynamic way, so that you can properly do your activity for the future. So this is the old topic we have already discussed in lot. Just to put in a in the sequence, I am just discussing. So we have discussed about different types of reservoir fluid we encounter. So, and in terms of what is their behavior pattern, their different parameters. Okay, dry gas, wet gas, volatile oil, black oil, heavy oil, bitumen. So if you see, we have discussed in details in our early classes. So if you have a light crude, if you have a heavy crude, if you have a condensate, or if you have a different types of fluid, how they will behave with time, how their property change with the production type. Okay, so reservoir architectures. Now another part which is important, that means how logically from the well information and the seismic information or geophysical information we are trying to reconstruct our structural model. Okay, reservoir architecture. Is it a flat type? Is it a tilted type? Anticline, dome, heavily faulted? That means each and every part of your reservoir should be properly understood for the dynamics of the reservoir. Okay, so you may draw, you may develop contour map, you may draw cross sections, you can develop log correlations to understand how the three-dimensional actual configuration of the reservoirs is. Okay, so once you understand, then you can do much better way. Okay, so major types of permeability and porosity distribution. So depending on the type of geological background informations of the reservoir, you see if it's a homogeneous, layered reservoir, cyclic reservoir, jigsaw pockets. Okay, so what these are all the result of a sedimentary environment of deposition. As we have studied the sedimentary environment of deposition, that's why we need to see what are the environment of deposition of this specific sand, pay sand. Is it from a specific type of sedimentary environment? So that can give us some idea about the nature of the specific pay sand, and if I have some specific information, I can upscale this information into my reservoir scale. So this is how geology background or information should be put into our system or architecture development of our specific reservoir. Heterogeneous permeability and porosity. So now you try to understand our different reservoir segments. Okay, so if I distribute so multi-layer reservoir, you have a randomly heterogeneous reservoir, you have a lenticular reservoir. That means depending on the type of your sedimentary environment where this specific pay sand is deposited, that would be the guiding factor to understand your reservoir architecture. Once you understand your geology, background geology of this environment of deposition of this specific pay sand, then it would be easier for you to upscale. So we may have a very small information. We may have one well information, we may have multi-well information, but that actually you can just see the same informations can be interpreted in different ways. So we have only well information. You see 1, 2, 3 same. Here you see the same information, but you may have an area where you could not look into it. You cannot see it, but it's your assumption, or you can see your prediction, so that you are extending the sand body. Okay, so this is how it's very important in each and every well. Here if you just go through all the layers here, in the well informations are exact in each and every cases, but depending on your understanding about the reservoir, how you are upscaling this well information to the reservoir scale. This is most important part in terms of upscaling the information into the three-dimensional information. Okay, so layer reservoir, these are different types of logs you are using. Okay, so here this is a well informations. You may have a multi-well where from gamma ray log, then your resistivity log. Okay, induction log, actually this is IL. So different way we are trying to correlate 1, 2, 3. So now depending, so that what one is sedimentary environment, second is your well log. That means what geological informations are properly put forward to understand specifically the. So if you just see here layered reservoir architecture, if you are getting in 1, 2, 3 the similar type of your information, that can be put here. But if you are missing out certain information, let's say well 3 having this, but well 2 and 3, so how long you will extend, that is your understanding about the reservoir environment of deposition of the specific reservoir. So this is now some part is there which you have to predict, but that should be properly backed by your geological information or other information. Okay, so here the same thing you see, this part based on your, because how you visualize your structures of your specific pay sand or reservoir, layer reservoir, so that actually gives you the basic output or main output for your development program or plan. Okay, so depending on how layers are connected and the permeability of individual layers, the production profiles for individual wells may be similar for well in the same area or structural position. So this is what, these are very important aspect when you are visualizing. So it is not very easy part to just say it is very so when you are combining the data, that means you are trying to visualize each and every data properly to understand. Okay, so this is what the sequence of water cut increase. So when you are having a production profile, here you see water cut. Okay, so how basically in three-dimensional configurations your GOC or maybe your WOC, all the parts are moving, and how each and every well is giving you the production profile. That gives you the aerial view how the OWC or your OWC is moving up, or you have a specific pattern of flow in a specific well. That means individual well production data will help you to understand the reservoir performance. Okay, now these are a single layer reservoir, you may have double layer reservoir, you may have a jigsaw reservoir. So depending on the different water sweep efficiency, so what variations in the permeability are different. So depending on the mobility ratio for injected fluid and displacing fluid, so displaced and displacing fluid, your this particular movement of the water and oil front may not be very piston type. So depending on that, you may have different types of features. That means you may have residual oil left out due to this high mobility of water. Okay, so that's why, and each layer is having different permeability values. So that's why same flow pattern will not be followed. If you see here the two layer, here you see oil movement is not that fast, where the water is moving very fast here. Okay, so that means this will be happening in each and every layers, because they are not homogeneous in nature. So this sort of things you need to predict by your own way. So just I'll move little quickly for this. Okay, so that means what? Open a carbonate or an intermediate low permeability sandstone, there are zones. Whatever is written there, there is nothing but just if your reservoir having specific type, then what should be the, how do you understand? So regional variation in production profile, in if injection processes implemented, there are uniform, that is what should be the production profile, or what should be the feature once you do or you encounter this sort of reservoir. Okay, so this is reservoir. So if you fracture reservoir, you know what is a fracture. So sometimes as a faulted reservoir, fractures may show up in course. So you may understand highly variable production rates with the best well producing much more than expected based on matrix porosity. Okay, so that means you have an irregular flow, one through the fracture and another through the matrix. So that means where the fracture density is more, you may encounter more flow. Where the fractures are not that dense, so you may not get. So that means depending on the pattern of your fracture and matrix permeability, you may encounter different flow rate in very closely spaced wells also. So the very rapid water and gas breakthrough if fractures are connected. What is happening once the fractures are there, the flow is very fast. So that's why once you are trying to draw down more, so water will move very fast or gas will move very fast and they will produce. So production fractures detected in production logs or interference tests. So these are what, how do you judge? By doing certain analysis. So that's why I'm saying that whenever you are predicting or visualizing something, how to test that or how to confirm this, okay, whatever you are predicting, that is for sure. So that's why data acquisition and proper planning of your specific data acquisition should be very important. So knowledge here is very important here, how to go ahead. So if you have a tight reservoir, you could understand tight reservoir, you need to improve the permeability around the wellbore, you need to create fractures also. So reservoir may be self-sourcing, that is the hydrocarbon may come from organic material within the rock matrix, so that the well log overestimate available porosity. These are actually, you may be studying in your well log for that. Some of the cases we may overestimate porosity due to, let's say, presence of clay minerals or sometimes. Okay, so that's why each and every subject of data acquisitions having advantage and disadvantage. So once you are going for a specific type of work, you should be at least you should know what are the basic principles for data acquisition in this specific way, and what are the advantage and disadvantage. So because you are actually collating all the information for understanding your reservoir performance in much better way. So this is what critical parameters for different drive mechanism. Already we discussed when we study our drive mechanism. Okay, so expansion drive, your analytical tool. So if you have expansion drive, that we have already discussed. If you have gas cap drive, so how you just try to understand your reservoir performance. So these are what we discussed this one. So when you have an expansion drive, what are the features you will encounter? Because you see, when you start taking production of an expansion drive or a solution gas drive, what is going to happen? It will come to a bubble point pressure in a specific point, then the gas will come out and they will start giving you a support if you don't produce it. So that means if you have an expansion drive, so how to know or how to keep the pressure higher? If you have a solution gas drive, then what to do with the solution gas drive? You may have a gas cap drive, we have discussed. So how each and every drive mechanism is supporting you, because we have discussed many times, the actually depending on the drive mechanism we need to plan for our production profile. Okay, so this is what, if you see a gas cap drive, the initial pressure equal to the bubble point pressure, but once you increase your production profile or production rate, your pressure will automatically decrease. Once you decrease, so gas will come out, and gas is highly mobile, so that's why they will start taking production. Okay, if OWC is present, there is no evidence of water encroachment. Okay, so that means how you see your drive, you may have a drive, but drive may not support your production. So that's why initially you may not predict that part. Structurally water is present below of your reservoir, but that may not be supporting. So once you do your testing, well testing, transient well testing, that may help you sometimes to get, okay, if the driving mechanism is there, drive is there, is it supporting, and if it is supporting at what rate. So that is also an important part. So the ultimate oil recovery is in water drive or gas cap drive case is this we have discussed. Okay, so now what? So that means you are trying to understand initial part, you may not understand your drive mechanism. If you have water drive, you know water drive may be of different types. It may be a bottom water drive, it may be edge water drive, it may be partial water drive. Even if you have that, then how it is supporting? Is it supporting your the right way? If you have strong support, then hopefully your production profile would be very good and you can predict. So you can see the ultimate oil recovery is between 20% and 80%. So the material balance is dominated by water influx. So that means we have discussed during our material balance discussion. So production profile, pressure value. So if we remember, we have a specific formulations for specific type of reservoir. We are plotting different production value with pressure, maybe sometimes water curve, maybe sometimes with time, and try to understand how the shape of the graph is changing. Okay, and that gives us some idea. Oh yes, it is water influx is there and is supporting in a very nice way. Okay, so that actually help us to understand and then plan for our production profile for the future. Okay, if you have a combination drive, also you may, and when you have a combination drive, you need to understand what support is giving pass. Is it water or maybe gas cap? So, and what is the support system? Is it a very generally strong support system? If it is there, only one support. But if you have a combination drive, always there is a weak combination drive of combination drive, and both the support is weak. That's why it's a combination. It may be a gas cap, it may be weak water drive support, and the ultimate recovery is also maybe high in some cases depending on the support system existing into your reservoir. Okay, so now how do you understand? So this means with time, combining our petrophysical information, fluid information, well test information, production value, we are trying to understand, and we are trying to understand the support system. So how we characterize our flow? So if we just see it here, you see we discussed, we may have a horizontal well, we may have a vertical well, and how the flow is occurring we discussed also when we are doing the well test analysis. That help us to understand different types of flow. That means the flow regime, it may be a radial flow, it may be an elliptical flow, it may be a linear flow, bilinear flow. That help us to understand different types of flow support or support during the flow right from well to our reservoir boundary. So gas cap, water legs and injectors will give reservoir pressure support in producing well. So how do you understand? Because it is not only the production profile. Sometimes you are using injection well to understand how the flow pattern or the flow is going towards the production well, or how communication is established between the two wells, so that if I inject water into the injection well, that can easily go towards the pushing the hydrocarbon towards the production well. So uniform flow occurs in homogeneous reservoir. Many analytical methods apply to uniform flow reservoir. So now we use different advanced technique to understand the flow part. Sometimes the well test analysis help us, sometimes tracer. We should inject tracer to understand, or sometimes now many new ideas are coming up by different types of material. We are injecting with the injection fluid and trying to trace them how far they have moved to inside the reservoir. The extent of gas segregation has a sufficient impact on solution gas drive, gas cap and combination drive. So we discussed about this part earlier. So when your gas is coming and you are allowing it to flow, then you are actually losing your energy of the system. So now what happens if gas is coming and you have a top perforation? So you close the perforation so that your gas should be stored on the top, and as gas is highly compressible in nature, they will help us in the driving energy. Okay, so this is how with time you may have to work for your optimum reservoir production. Consistency check and the choice of analytical technique. So this is how do you go for your analysis? You can see a reservoir is well delineated with wells but has limited pressure data. The volumetric material balance. So that we have discussed when we discussed about the reservoir engineering principles. What should be followed? So volumetric you can do anytime, but you cannot do your material balance when you didn't start your production. Okay, so should be given to volumetric oil initial in place should be in the very early stage. But once you start taking production and you have recorded your pressure and the production data, that time you can use your reserve, volumetric reserve estimation. And once you get the decline started, that time you can use your decline curve analysis. But with the initial stage also and simulation also, we could do the simulation to understand different analytical techniques, how to do the analysis, okay, for your reservoir performance. Model errors, mainly three components. So once you are preparing a model, I told you it's a static model, it may be a geological dynamic model, okay, it may be a mental physical mental model, okay. So errors in data caused by inaccuracy and imprecision by the measuring device or human error. So this is very important part. Once you know your subject and limitation of the data acquisition, then you can properly predict it. So what generally people do in this industry, many people are expert in their own field but may not be knowing the other field. So that's why it's very important to validate the data. We have plenty of informations, but sometimes the informations are garbage in nature. So being a scientist and engineer, you must be careful by validating the information which you have in your hand. Error is a result of the model being simplifications in the physical system. So when you are trying to visualize, if you are not an expert geologist, sometimes your interpretation may not be wrong. If you are not an let's say dynamic well test analyst, you cannot be properly understand a physical nature. So sometimes proper utter simplification of the data or the information may be leading to an erroneous result in your production. So that also may happen. Error due to neglecting physical phenomena. So some information is evident in the data, but as you are not an expert, you could not properly analyze this information. So sometimes this also, the phenomena is occurring, you could gauge it from the production data or maybe the pressure data, but you could not incorporate the proper physical significance of that specific information. Okay, so static model and the flow simulation dynamic model, the second type of errors occur. The other problem can be, so what in the whole system actually validation of informations should be proper, so that the group members should put together their all the expertise to come up with a good model, so that it is devoid of very limited or maybe devoid of errors, maybe very limited errors are there. Okay, so this is how a team members are planning accurately or properly, putting their wholehearted effort to understand particularly the geological and the dynamic model. So this is what we are trying to understand, how we are trying or how we characterize our reservoir based on the data which we acquire through well log, through core petrophysical information, through lab study. Then we may have some core flooding study also. We may have the PVT, proper sample collection PVT study. Then we may go for the transient well testing for specifically analyzing our reservoir. So it is not that data acquisition is important. After the data you acquire, you need to see a lot more information which are already there in the system. It may be from the geological informations by the seismic study, or maybe from the during the drilling time from the well log informations. Okay, so every people have put their effort, and now what, being a development geoscientist, we need to take care the proper data and then validate the data and then put properly for our developing our different model for characterizing the reservoir. Okay. So for today's discussion, we have just sum it up for characterizing reservoir using all the data we have. So